Vectors can be used particularly in physics for force, electricity, and magnetism. Just mathematically, though, we draw an arrow. That's at least a geometric description. Another description that we use in math is just a comma separated list of numbers and angle brackets. So I know that vectors tend to be a thing that people freak out over. And I think it's the connection between the algebra and geometry, or just because it's new, but really, as far as just on paper, at least a non-geometric way of describing vectors, it's just a bunch of comma-separated numbers in angle brackets. You're used to comma-separated lists of numbers in parentheses, but now it's just in angle brackets, and you do some different manipulations with it. That's all. You just, we had the vector addition from last time, for instance. So I think just realizing it's just a bunch of numbers in a certain order, separated by commas in angle brackets, helps make it so that vectors are not so bad. The connection between the two takes a little bit of convincing, but if you get through that, then vectors are really awesome because you get to draw without drawing. Just remember that a vector, though, in its sort of definitional sense, I'm not going to ask for a definition, but just vector is a little elusive. And I think for now it's just good to remember that a vector has both a direction and a magnitude. And that you can see a little more apparently in the geometric version. So a number or a scalar, these words number and scalar, I'm going to use these interchangeably. So a number or a scalar is like x equals 5. And even in the notation here, notice this x, it's just like a good old standard x that you write in math notation. Versus a vector, either I would write a normal handwritten A with an arrow above, or the book style is to write a bold A. And then, well, for a specific example, like we saw the constant or the scalar 5, now here I have 3 comma 4 in angle brackets. Okay, so given a vector, its magnitude or length or norm, please recall, is its notation. One of them is a double vertical bars. You could use single vertical bars. It's your preference. I will accept either. It's a formula that looks based on the Pythagorean theorem because that is honestly where it comes from. And recall from last time, vector addition is component-wise. By the way, a vector plus a vector results in a vector. And geometrically, there was that parallelogram thing we saw. Scalar multiplication, it's what's really going on, just in a nutshell, is a scalar times a vector becomes a vector. Right? So you need a scalar and you need a vector, and then you get a vector out of this. So it looks like this. That was the formula that defined it. And in terms of for us, there's a new operation. So I wanted to compare this to the old one. Scalar multiplication was a scalar times a vector is a vector. Our new operation starts with 2 vectors. So given a vector u and a vector w, the dot product of u and w looks like this. So we wrote just in the notation or symbolic form here, like using its label, vector dot vector, and then I just wrote it out. I just did a little replacement of the u vector from how it was defined up here. Same with the w vector. And then what is it defined to actually be? Well, you multiply the first components together, you multiply the second components together, and then you add the results. So what you end up with actually ends up being a scalar. So you must draw the dot. Just putting the 2 vectors next to each other, I know that very often in previous algebra land, you would just put one thing next to another and multiplication was assumed, but there's going to be another operation next time. So we have to be careful. The dot product, what does it result in? It really is a scalar. You'll see in the example. But just to summarize, the difference is that a dot product is a vector, then dot, a vector, results in a scalar, as opposed to earlier scalar multiplication is a scalar times a vector results in a vector. So here's an example, vector 3, 2 and vector negative 5, 11. Let's find the dot product. Here's how it goes. I take the first components of 3 and negative 5, multiply them together. Take the second components of 2 and 11, multiply them together. Add the result. You end up with the number 7. You end up with a scalar. Okay, so the final result of the dot product and the scalar, in this example, that was 7. The dot product, therefore, is also called the scalar product. If you're in linear algebra, the dot product is an example of a thing that's called an inner product. Sometimes in a linear algebra, towards the last week of the semester, you might get around to this topic called inner products. I just mentioned it just for fun, just kind of, what do you call it, like just a little factoid. You would never get quizzed on this in this class, and very often a linear algebra class doesn't even get around to talking about inner product. Okay, and then if you take 2 vectors in 3-dimensional space, can you find a dot product? Even though we didn't formally present the formula, it's exactly what you think it is. It's the sum of products. So multiply first components together, multiply second components together, and now multiply third components together. In this example, the dot product of 1, 2, 3 and 4, 5, 6 ends up being the scalar 32. Right? So though we didn't cover it, the formula for the dot product of two 3D vectors is exactly